Okay, so as string theorists, we've been very, very good at understanding things that are asymptotically flat or asymptotically ADS, but it's critically important to do things that are asymptotically de Sitter, and so it's delightful to hear from Scott Collier on a matrix model for 2D de Sitter gravity.
Okay, great. Well, I'd like to start by thanking the organizers for the invitation and putting together this really wonderful workshop. I'm looking forward to discussing with people over the course of the week. So today, I'm happy to tell you about this work in progress that we've been doing together with my outstanding collaborators, Lawrence Eberhardt, who's here, Beatrix Muleman, and Victor Rodriguez. So let's get into it. There is a stark dearth of precise, controllable models of de Sitter quantum gravity. Okay? And in some sense, this highlights a shortcoming in our current formulations of string theory. Now, we've learned a lot in recent years by studying solvable models of ADS quantum gravity in low dimensions. So a natural place to start is 2D de Sitter. And indeed, in recent years, there have been a variety of different approaches to DS2 gravity, but I think it's fair to say that no clear unifying picture or new conceptual framework has emerged. Now, about 5 years ago, Saad, Schenker, and Stanford taught us that ADS2 Jakiv-Teitelbaum gravity is dual to a double-scaled random matrix integral. And recently, this duality has been embedded in string theory, where, in particular, JT gravity has been realized as a semi-classical limit of the worldsheet theory of the 2, p minimal string and of the recently discussed Virasoro minimal string. And you can think of this as placing this JT-RMT duality in an older tradition of dualities between low-dimensional models of string theory and random matrix integrals. So it's natural to wonder whether there could be a similar stringy realization that involves DS2. So in attempting to formulate models of DS2 holography, it's a natural terrain for exploration is this paradigm between low-dimensional models of string theory and double-scaled matrix integrals. So the 2D string theory is defined by coupling some matter CFT with central charge C to Liouville CFT with central charge 26 minus C. And in many situations, these models are dual to double-scaled matrix integrals. These are theories involving some matrix M, some n by n Hermitian matrix, which you integrate with some potential. Now, the dualities emerge in the double scaling limit, where you take n to infinity and zoom in on some region of the spectrum. And these models are fully characterized by what's known as the spectral curve of the matrix model, which in particular encodes the leading density of eigenvalues. So, these matrix models admit a topological genus expansion, and all the quantities in this expansion are fixed by this spectral curve. So here's a cartoon of this incomplete two-dimensional landscape of string theories and matrix model dualities, and let's discuss a few of the entries in turn. So the simplest is the 2, p minimal string. This is defined by coupling a 2, p Virasoro minimal model to Liouville CFT. And these occupy a discrete set of points on the negative C axis. And it's been known since the 90s that these models are dual to double-scaled matrix integrals, with this rho 0 of E specifying the leading density of eigenvalues. Now, recently, it's to some extent been understood that in the p to infinity limit, in which the central charge of the minimal model CFT goes to minus infinity, JT gravity emerges as a semi-classical limit of the worldsheet theory. And indeed, this leading density of eigenvalues reduces to this sinh root E density of states that has appeared in the JT discussion. Moving on up, we have the p, q minimal string, which is of course defined by just coupling a more general p, q Virasoro minimal model to Liouville CFT on the worldsheet. And these carve out a dense set of rational points in the C less than 1 region. And it's been known for some time that these models are dual to double-scaled 2 matrix integrals. So they involve integrals over 2 matrices. And the spectral curve of these models is given by these Chebyshev polynomials, which depend on the p and q of the minimal model. Now, at Strings last year, Lawrence told us about the Virasoro minimal string. This model is, again, a 2D model of string theory defined by coupling Liouville CFT with any value of the central charge C bigger than 25 to time-like Liouville CFT with central charge 26 minus C. And in a paper from the fall, we showed that this model is precisely dual to a double-scaled matrix integral whose leading density of eigenvalues is given by this sinh formula, which for the experts is related to the Carty formula for the asymptotic density of states in 2D CFT. Now, the observables in this theory were the string amplitudes turned out to simply be polynomials in the scaling dimensions of the vertex operators. And you can think of them as deformations of the Weil-Petersen volumes of the moduli space of Riemann surfaces. And indeed, in the limit where you take the central charge of the Liouville CFT to infinity, or this B parameter to 0, this model reduces to JT gravity on the world sheet. And indeed, we call these VGNs, the quantum volumes. They precisely reduce to the Weil-Petersen volumes in this semi-classical limit. So today I'll discuss a new entry in this landscape of low-dimensional string theories and matrix model dualities that we're very tentatively referring to as the Liouville squared string, but we are definitely on the market for better names if anyone has one. So it involves coupling two copies of Liouville CFT with complex central charge, and we'll be particularly interested in the regime where the real part of the central charge is 13. So that the two Liouville CFTs can, in a sense, be thought of as complex conjugates. And today I'll try to argue that this model is precisely dual to a double-scaled two-matrix integral, which is characterized by this spectral curve with these cosines. Now, the observables in this theory, the string amplitudes, we call them AGN, and they're much more complicated than the volumes that appeared in the Virasoro minimal string. In particular, they're no longer simply polynomials, and they involve some infinite set of poles and discontinuities viewed as functions of the external momenta. But the duality with the matrix integral will allow us to compute them exactly using topological recursion. OK, so here's a roadmap for the talk. If you remember one thing, it should probably be this slide. So I'll describe a duality today between this two-dimensional string theory, which involves coupling Liouville CFT on the world sheet, two copies of Liouville on the world sheet, with a double-scaled two-matrix integral. And the loop equations of the two-matrix integral will translate into some topological recursion relation for the string amplitudes. Now, this world sheet theory admits a semi-classical description in terms of a priori simpler theory of gravity. In particular, we'll show that it can be formulated in terms of a model of 2D dilaton gravity with a certain potential for the dilaton. And what's intriguing about this formulation of the model is that it admits vacua that are both ADS2 and DS2, so solutions with both signs of the cosmological constant. So I want to argue that this story I'm telling today can be thought of as a precise and controllable holographic duality that at least includes DS2. So here's the plan for the rest of the talk. I'll discuss the worldsheet theory and its relation to sign dilaton gravity. I'll then move on to discuss the observables in the theory, the string amplitudes, and how we can essentially bootstrap them from the exact solution of Liouville CFT. And then I'll conclude by discussing the dual matrix integral and how topological recursion allows us to compute the string amplitudes. So let's get right into it. Now, the two Liouville CFT admits a Lagrangian description in terms of some scalar field, say phi. So when we take the two Liouville CFTs involved in the worldsheet theory, it turns out that there's a simple field redefinition that, at least at the level of the classical action, rewrites the model in terms of this theory of 2D dilaton gravity with assigned potential for the dilaton. So we'll discuss today this model on generic Riemann surfaces sigma. And it's a theory of a dilaton capital phi and a 2D metric G. And it involves this by now familiar linear coupling between the dilaton and the Ricci scalar, together with this sign potential for the dilaton. And what's interesting, at least for sufficiently generic surfaces, the solutions of this model correspond to zeros of the potential. In particular, there's this infinite family of classical solutions which are constant in phi, labeled by this integer m. So on shell, the Ricci scalar is fixed to be minus w prime of phi on these classical solutions. So you end up with a cartoon that looks like this. Here I've plotted the potential sign of phi in black and minus w prime in red. And what we see is that on shell, the Ricci scalar alternates between positive and negative solutions. In other words, the classical solutions alternate between DS2 and ADS2. Now, what kind of solutions am I discussing today? I'm discussing solutions where phi is constant on some surface sigma. But because the solutions correspond to constant phi, I can also consider degenerated surfaces where phi takes different values on either side of the degeneration. So you can have situations like this bottom drawing here, where phi takes different values labeled by M1 and M2 on either side of the degeneration. And in this sense, you can think of this model as hosting something like transitions between universes, between DS2 and ADS2. And I should mention that the DS2 solutions should be thought of in minus-minus signature, as in a recent discussion of Collier and Jensen. OK, this dilaton gravity picture is nice, but I won't really make much use of it for the rest of the talk. Instead, I'll do string theory. And we'll be equipped with this non-perturbative exact solution of the worldsheet theory. So we should think of the worldsheet theory as being defined by the CFT data. In Liouville theory, we like to use this B parameter for the central charge, say for the C plus theory. And here, for these values of the central charge, this B takes values with this funny pi over 4 phase. The spectrum of local operators is spanned by a continuum of scalar primary operators whose scaling dimensions are fixed in terms of this quantity little p that's sometimes called the Liouville momentum. And finally, the OPE data, or the structure constants, are fixed by the 3-point functions of primaries on the sphere. So these are given by the famous DOZZ formula, which was bootstrapped by, DOZZ, culminating in this explicit formula, which is some meromorphic function of the momenta. So together with the CFT data, we can compute any local observable in the theory. So any correlation function of local operators on these surfaces. So let's discuss the observables of the theory now, the string amplitudes. So as I mentioned earlier, I'll focus on the choice where this B parameter has this funny pi over 4 phase, which corresponds to the central charge having real part 13. It turns out to be both interesting and convenient to consider the situation where the Liouville momenta have this opposite pi over 4 phase. And this corresponds to conformal weights with equal to 1/2 plus IR. And this is kind of interesting. We think you can think of this as a sort of Virasoro analog of the principal series representations of SL2C, the Euclidean global conformal group. So as usual in string theory, we form on-shell vertex operators by combining primaries in the two theories. And in the situation where we cancel the Weil anomaly so that the central charges add up to 26, and solve the mass shell condition so that the conformal weights add up to 1, then these two operators are in some sense complex conjugates of each other. And indeed, the observables in the theory, which up to normalization are defined by integrating the correlation functions of Liouville CFT over the moduli space of Riemann surfaces, these two correlation functions are complex conjugates. So the moduli space integral involves an absolute value square. Moreover, for these choices of parameters, this integral over moduli space turns out to be absolutely convergent, which is nice and not often the case. Finally, these amplitudes are invariant under a swap symmetry, where we send B to minus IB and P to IP. At the level of the worldsheet theory, this is essentially tautological. It just amounts to swapping the roles of the two theories. But in the bootstrap approach we'll take to solving for the string amplitudes, this will turn out to be a non-trivial constraint. Now, the simplest observable in the theory is, of course, the sphere 3-point amplitude, because in this case, there's no moduli space to integrate over. So up to normalization, this is just given by the product of DOZZ formulas in the two cousin theories. And actually, this combination of DOZZ formulas was studied by Zamolodchikov in 2005. And what they found was that the result is some elliptic function viewed as a function of the momenta. You can write it in terms of Jacobi theta functions. We won't need that here. Instead, it will be convenient to write it in terms of this infinite sum over this integer m, which ranges from 1 to infinity. And you can loosely think of this integer m as labeling the classical solutions that I discussed in the dilaton gravity picture at the beginning of the talk. Now, more general string amplitudes are, of course, as I mentioned earlier, defined by integrating correlation functions of Liouville CFT over the moduli space of Riemann surfaces. And this is, of course, a tremendously complicated task. Even numerically, you can only really hope to carry it out for sufficiently low g and n. On the other hand, we know all there is to know about Liouville CFT. So I'll advocate leveraging this exact solution of Liouville CFT to deduce the analytic structure of the string amplitudes. And together with this swap symmetry and some other small assumptions, you can essentially bootstrap the amplitudes without actually having to carry out the moduli space integral. With respect to the analytic structure, what we'll find is an infinite series of poles corresponding to resonances of the Liouville CFT correlators, along with an infinite set of discontinuities, which arise when one discusses analytic continuation of the external momenta away from the regime where the moduli space integral converges. So remarkably, what we found was that the solution to this bootstrap procedure could be systematically implemented with some extremely simple diagrammatic rules. You can kind of think of these as like Feynman diagrams for the string theory. What we found was that the specific Feynman diagrams, individual Feynman diagrams, corresponded to particular degenerations of the world sheet surface. So you can think of the Feynman diagrams as being formed by a number of components, or vertices, each of which is itself some Riemann surface, which are then glued along degenerating points. To each of these components of the Feynman diagram, we associate an integer, which we then sum from 1 to infinity. Again, this integer is just labeling the classical solution in the dilettante gravity theory. We also, intriguingly, find that each vertex receives a factor proportional precisely to the Virasoro minimal string quantum volume, which plays the role as a string vertex. So it's interesting that the VMS quantum volume plays the role of a building block of the string amplitudes in this Liouville squared theory. So to make this concrete, I think it's useful to discuss a specific example. Let's look at, for example, the sphere 4-point amplitude. In this case, there are two topologically distinct Feynman diagrams. There's one that just involves the sphere 4-point vertex on its own, so there's just one sum over this integer to do. And there's another that you form by gluing together two pairs of pants at this nodal point. So in this case, there are two integers to sum over. So the way the Feynman rules work is there's some normalization factor associated to each primary. There's a vertex factor, which, as I said earlier, is proportional to the Virasoro minimal string quantum volume, which is just some polynomial. And finally, for each degeneration, we integrate over the internal momentum, weighted by this factor. And we claim that this is the full answer for the sphere 4-point amplitude, which exhibits the correct analytic structure and satisfies all the other consistency conditions. This can be carried out as well for example, the torus 1-point function. And again, here there are two simple classes of Feynman diagrams, but let me not dwell on this for now. So in these situations, specifically for the sphere 4-point function and torus 1-point amplitude, the moduli space integral can be carried out numerically, directly. So here's an example for the sphere 4-point amplitude where we pick some random value of the central charge with real part 13, and essentially random values of the external momenta, and then vary one of the magnitudes of the momenta. And we find a remarkable degree of agreement between this direct numerical integration and our ansatz from the Feynman diagrams. So we have a great deal of confidence in this. Just to drive home how this works, here's a slightly more non-trivial example where there are more classes of Feynman diagrams, the torus 2-point amplitude. So again, there's a torus 2-point vertex, which just involves a single sum, proportional to V12. And then you have to sum over diagrams that enumerate the different ways the world sheet surface can degenerate. So the first example here on the right is one where you take a pair of pants, degenerate one of the legs, and glue it to a one-hole torus, and so on and so forth. OK, so that's it for the string amplitudes. Now I will discuss the dual matrix integral and how topological recursion can be used to compute the string amplitudes. So the central claim of this work is that this Liouville squared string theory is precisely dual to a double-scaled 2-matrix integral. So again, this is just some integral over n by n Hermitian matrices with some potential and some minimal coupling between the two matrices. And the double scaling limit, we take n to infinity and zoom in on some region of the spectral curve. And we claim that this matrix model is characterized by this spectral curve with these cosine formulas for x and y. And one feature of this matrix integral is that it has infinitely many branch points, or infinitely many sheets. From this, one can extract the leading density of eigenvalues of one of the matrices, say M1, which I'm calling x here. Up to normalization, this is given by this sine minus IB squared arc cosh x formula, which a priori is supported for x bigger than or equal to 2. But you'll notice that it involves a sign. So the way we're thinking about it right now is that The spectrum of eigenvalues should be defined as living between 2 and the first 0 of this leading density. But once we discuss deforming the contour of integration and the integration over the eigenvalues, then we're in the realm of non-perturbative effects. Now, as I said at the beginning, these matrix integrals admit a topological expansion. So for some observable, say the resolvents, there's a topological recursion fixed entirely by this spectral curve that computes all of the exponent or all of the perturbative expansion data. And indeed, it was the sum over Feynman diagrams, the structure involving the degenerations of the Riemann surface, is precisely analogous to this topological recursion, say for the resolvents in a particular way of writing things. Now, we can translate this topological recursion, or the loop equations for the matrix integral, into a recursion relation for the string amplitudes themselves, very much in the spirit of Mirzakhani's recursion relation for the Weil-Petersen volumes, which showed up in JT. So the way it works is the following. Suppose you want to compute some general string amplitude AGN. Then the recursive formula involves some integral over two internal momenta, Q and Q prime. There's a recursion kernel that I call H, and a factor of the sphere 3-point amplitude, A03. And this corresponds to a particular distinguished pair of pants that involves this special label that I call P1, but you could have picked any of the external momentas if you wish. And then we sum over the topologically distinct ways of embedding a pair of pants with this distinguished leg into the surface. So you have these non-separating embeddings, which reduce the genus by 1 and adds an extra boundary. There are the separating embeddings, which roughly split the surface into 2. And finally, there are these embeddings where the pair of pants includes one of the other external legs. And then you get a factor of the string amplitude of lower complexity that comes from this embedding of the pair of pants. And then you sum over them and carry out this integral. Now, I should remark that Lawrence presented an essentially identical recursive formula for the quantum volumes of the Virasoro minimal string last year at Strings. In fact, even the recursion kernel H in the bottom left here is essentially the exact same as the one in that recursive formula. So what's different? The only difference in these formulas is this sphere 3-point function that I discussed at the beginning of the talk, this A03, which is some non-trivial function of the 3 momenta. Whereas in the Virasoro minimal string, that was just 1, as it is for Weil-Petersen, for the 3-hole sphere. And I should mention that this recursion kernel is you can think of it as a deformation of the recursion kernel that appeared in Mirzakhani's recursion relation. Now, of course, there's more to life than perturbation theory. In principle, we should be summing these string amplitudes over genus. And that sum is presumably asymptotic, which would signal some non-perturbative effects in the dual matrix integral. And these correspond to ZZ instanton effects in the string theory. I won't have any more to say about them as I'm almost out of time. But let me just say that qualitatively, they seem to be quite different than the ZZ instantons that we computed in the Virasoro minimal string in the way that they alter the eigenvalue spectrum. OK, with that, let me just remind you of the big picture of what I've told you about today. So I've tried to advocate for this precise holographic duality between this 2D string theory that involves coupling 2 copies of Liouville on the world sheet and a double-scaled 2-matrix integral. I discussed how the loop equations could be used to compute the string amplitudes recursively. And finally, we drew a connection with this sign dilaton gravity theory, which admits both ADS2 and DS2 vacua. So there's some sort of big picture questions we could ask, like, can we ever get DS2 on its own? Are we learning something deep from the fact that DS2 had to come paired with ADS2? And so on. I'll conclude here, but let me just leave. I couldn't resist putting some sort of open-ended questions at the end, and I'll say thanks very much for your time.
Questions? Way over there.
Can you go to slide 24?
Slide 24. I can.
So in the density of eigenvalues, is there a simple property of this formula that captures minus minus ds2 physics?
That's a good question. Not intrinsically. You might be tempted to assign some importance to the fact that the eigenvalue spectrum is cut off at the zero of the density of states. I don't want to dwell on that, but not as far as I can say right now.
And is this complex?
Is this complex? No, it should be real. IB squared is real.
So let me ask you, so you mentioned that you can find the sitter and anti-de sitter.
Yeah.
But I didn't understand the physical meaning of all these string amplitudes from that point of view.
They're
What are we
computed by
computing?
the gravitational path integral of this sign dilaton theory.
But what are we computing, say, in the sitter 2 that corresponds to this string?
Yeah, I don't know if there's a question you can ask only in de Sitter to which these string amplitudes are the answer. The path integral involves some sum over all of these classical solutions, which involve both DS2 and ADS2 classical solutions. But many of these conceptual points we're still sorting out, to be honest.
There's a question way up the back there.
Nice thought, Scott. I think you may be able to justify your choice of the momentum, the phase that you put, if the linear dilaton has the same slope, has the same phase.
If the linear dilaton has
So your linear dilaton has to have to be complex, given your central charge. So
Can you say that again? Sorry?
if your linear dilaton has the same slope as that imaginary, as the phase that you're picking for momenta, you can justify it. I'm just suspecting that might be
B is related to the slope of the linear dilaton in the Liouville theory. It's roughly B plus 1 over B. The combination B times P is real here.
All I'm just saying is that the string coupling times e to the IPX should be the object you put. So the string
Yes,
coupling
that's right.
is running.
Yes,
Does
yes.
that give you the same phase you want or not?
I'm not sure in real time, but let's
Okay.
discuss after.
And the other question is that many of the suggested holography of de Sitter in higher dimension involves non-unitary duals. Is there a sense of unitarity or non-unitarity you have for these 2D models?
Well, Liouville CFT away from, going in the wrong direction, sorry. Liouville CFT in this regime of the central charge plane, it's a bit confusing because now I'm discussing Liouville like it's the matter CFT, but bear with me, is only really unitary for central charge between 1 and 25. So as soon as I move away from that, the world sheet theory becomes non-unitary. But nevertheless, the combined theory on the world sheet makes sense, in the sense that you get sensible answers for the string amplitudes.
Thank you.
Could you go to slide 19?
Slide 19, yeah.
Yeah, so it says that the diagram corresponds to different degeneration of the worldsheet.
Yeah.
So I'm confused. What was the first term?
What was what, sorry?
Is the first term also degenerate Riemann?
Oh, no, it's the one without degenerations.
So it's that plus degeneration?
Yes,
Is
yes,
that-
yes. It's including the empty, the trivial one, if you wish, where you don't pinch any cycle.
Oh, okay, I see. So the other one, so the fact that the degenerate worldsheet appears is that, does that mean that somehow the integrand over the moduli space is a total derivative? Because that's how typically, for example, in Kodaira-Spencer theory, it becomes sum of a Feynman diagram. And the reason is that the integrand is total derivative.
That happens in some very special cases when you tune some of the external momenta, but in the generic case, I don't think so. That's an interesting question.
Thank you.
There's a question here.
So I wanted to belabor a bit on the point of unitarity. So you have well-defined amplitudes in the target space sense.
Yeah.
But is there a notion of unitarity? Are these amplitudes unitary in any sense?
Sorry,
Do we
sorry.
know, or?
Well, the amplitudes, I discussed a little bit these discontinuities of the amplitudes.
Yes.
They appear to obey the expected factorization properties when you cut one of the, say I cut this diagram along this degenerating point here. They factorize in a way expected. I actually have a bonus slide about this. So there's some structure with the discontinuities of the string amplitudes that is maybe expected from a target space point of view, but we haven't fully investigated it.
Thanks.
Okay, unless there are any other quick questions, let's thank Scott again.